Hi everyone, today we're going to talk about exponential functions. If you have something of the form f of x equals a times b to the x power, where a and b are real numbers and b is not equal to 1, then we have something called an exponential function. And so far in class, we've really only been looking at linear functions, so it's quite exciting to look at a new kind of function. Let's look at an example. It says, let's say that one day you come across a genie. A genie is a magical being that grants people wishes, and the genie offers you $1 million or a chessboard with a penny on the first square, 2 pennies on the second square, 4 pennies on the third square, 8 pennies on the fourth square, and so on. To make an informed decision, you should probably know that a chessboard has 64 squares on it. I've actually drawn kind of like a picture of a chessboard there. It's an 8x8 grid. And the question is asking, which offer should you go with? Let's explore our answer. So before we jump into part A, here's the scenario. So here's an example of a chessboard. On the first square, we would have 1 penny. So that'd be 0.01. And then on the second square, we'd have 0.02. On the next one, we'd have 0.04, 0.08, 0.16, 0.32 to represent 32 cents, and so on and so forth. And that pattern would continue on until the very last square. So part A says create a table where the input is the square number on the chessboard and the output is the amount of money on that square. So let's go ahead and make an input-output table. So the input is the square number on the chessboard. And the output is the amount of money on that square in dollars. So we have the first space, and that contains 1 penny, and then the second space that contains 2 pennies, and so on and so forth. It doesn't seem like this would be that great of a payoff, right? Like these numbers are kind of small. So on the 8th square, there'd be $1.28. The 9th square, there would be $2.56. And on the 10th square, there would be $5.12. So now that we've made this table, maybe take a moment to pause the video and think to yourself, would you rather take the $1 million or would you rather take the chessboard with this amounts of money on it? Let's continue on. Maybe the next part will help us to solve that question or answer that question. So part B says, try to come up with a function that models how much money is on any given square. Now, I told you earlier that we were dealing with exponential functions, and those look like f of x equals a times b to the x power. Now, what is a power or an exponent? Well, if you've taken a math class before, you might have seen that that represents repeated multiplication. What do I mean by that? Well, let's say we had something like 3 to the 4th power. That is equivalent to 3 times 3 times 3 times 3. So we have the base here, and we have this thing called the exponent. And the exponent tells us how many times to multiply our base to itself. Now, how does that relate to what we're talking about here? Well, previously when we've talked about linear functions, we've looked for patterns in our input-output tables. And a lot of times the pattern would be that we would be adding or subtracting the same number each time we increased our input value by 1. So here, again, we are adding our input value by 1. So notice that it's increasing by 1. And when we do that, what is happening? What is the pattern in our output values? So how are we getting from here to here? How are we getting from here to here and here to here and so on? Take a minute to think about that. If you said that the pattern is that the output values are doubling, you would be correct. Notice that we are multiplying by 2 each time to get to the next value, and that pattern continues on throughout the table. So it turns out that in an exponential function, if our output values are doubling, what that means is in our function, our b value is going to be 2, because it's kind of like the equivalent of the slope in a linear function, but instead of adding, here we are multiplying. So that means that our function is going to look something like f of x equals 2 to the x power, but we still have to figure out what our a value is. What do you think it is? Take a minute to pause the video and ask yourself, what do you think the a value is? I don't know. When we dealt with linear functions, it was often like there were 2 components. There was the slope, and then there was the b value. And the b value was always related to the first value in our table. So if I'm just taking a wild guess, what if I just took this value and said, maybe that's our a value? Let's try it. 0.01 times 2 to the x power. Instead of putting a dot there, actually, I'm going to put a set of parentheses like that. So if that function was correct, then it would match and align with our table. So let's see if that's in fact the case. If I evaluated f of 10, then that would be 0.01 times 2 to the 10th power. So I would replace my exponent with 10 instead of x. Now, if you're not sure how to calculate that on your calculator, let me show you where your exponent button lies. Okay, so make sure your calculator is on, and then type 0.01 parentheses 2 to the power of 10, and then press enter. So this like caret looking button is how you get to the exponent, and it's above the the division symbol on a TI-84. It might be somewhere else if you have a different calculator. So now I'm going to press enter, and it gives me 10.24. Let's go back to our table. Notice that that's not what we have here, and so our function is not correct the way that we have it written. Now, hopefully you've noticed that when we dealt with linear functions, the way that we got the b value was based on the y-intercept, and so that required our input value to be 0. It works the same way with exponential functions. So what do you think if we plugged in 0, our output value would be? Well, notice that each time we are going up, we're multiplying by 2. So to go in the opposite direction, the pattern would be that we divide by 2. So that means that the value that goes under 0 is going to be 0.01 divided by 2, which is 0.005. And it turns out that that is going to be our a value. So this is the value that would go here. Let me erase the 0.01 that we have written. Oops. Okay, so let's see if that works. If we evaluate f of 10 now on our calculator, that would mean that we would do 0.005 times 2 to the 10th power. Let's go back to our calculator and see if that gives us the correct value that we want. So I'm going to clear it and write 0.005 times 2 to the 10th power. And our output is 5.12, which is what we had in our table, so that matches up. I want you to maybe plug in a couple more values. Try like f of 6 and f of 8 and see if those give you the correct values as well, but it should. So I'm going to go ahead and box our function now. So f of x equals 0.005 times 2 to the x power. Now part C says, use your function in part B to figure out whether you would choose the chessboard option or the $1 million. Now I told you that a chessboard has 64 spaces on it, so what we could do with our function is evaluate f of 64. What this is going to tell us is the amount of money that is on the 64th space of our chessboard. So that means that we'd have 0.005 times 2 to the 64th power. And let's throw that into our calculator and see what happens. So we have 0.005 times 2 to the 64th power. All right, so we plugged that into our calculator and we found that that was like 9.22337 E16. Another way to write that is 9.22337 times 10 to the 16th power, which if you don't know how multiplying by 10 works is every time you multiply by 10, you move the decimal point to the right one space. So if we're multiplying by 10 16 times, another way of saying that is we would move the decimal point to the right 16 places, which is a very, very massive number. To give you some more context, maybe let's evaluate f of 30. So that would be 0.005 times 2 to the 30th power. And I'm going to throw that into my calculator. So I threw that into my calculator, and on the 30th square, there is $5,368,709.12. Now, we are going to double that several times to get to the 64th space. So hopefully that kind of gives you some context about how just humongous this number is on the 64th space. So overall, we would definitely want to take the chessboard. That could end world hunger with that kind of money. So we would take the chessboard. And so, one thing about exponential functions, depending on what our b value is, our function's going to grow really, really fast. And so exponential functions are quite different than linear functions in that instead of adding or subtracting, we are multiplying by the same number each time.